Great. We're going to finish up on 7.2, okay, looking at the second part. And in this part, we're going to look at how we can take something that has trig in it and get rid of it and turn it into algebra. Now, in this class, that's not something we can do all of the time. Sometimes we have a formula, and it's going to have trig in it, and there's no way around that. What does an expression have to have in it to be a trig expression? What makes something a trig expression? Yep.
A trigonometric function.
Exactly. It has a trigonometric function. Sine, cosine, tangent, secant, cosecant, cosecant, any of their inverses. Anything like that is a trig expression. If you have like y equals x squared plus 4, no. That's just a quadratic equation. That's not a trig equation. There's no sine, cosine, or tangent in it. So what we're going to look at is taking an expression that maybe has trig in it, whether it's regular trig, inverse trig, or both, and we're going to see that there's a way we can get rid of all the trig in a pattern like this. Right? So I'm going to show you some steps on how we do that. And the goal is we're always going to start with the inside trig function. Okay, we're going to start with the inside trig function. Now, look at the one that we're going to do. The inside trig function is inverse cosine. First thing we have to remember is what is inverse trig used to find? When you type in inverse sine of something on your calculator and you hit enter, you get a number. What does that number represent? Yeah?
Like the y value for a trigonometric function.
So I'm thinking about if we connect it to a triangle. When we use inverse trig, say in a right triangle, what is the point of using inverse trig? It's used when you have to figure out what? Yeah?
The side of a triangle.
No, Pythagorean theorem is used when you're trying to find sides, or you could use a regular trig function like in Soccatella. But we don't use inverse trig functions in Soccatella when we do that. So what is inverse trig used to calculate? Yeah, angles. Angles. That's what inverse trig is used to figure out. Okay, so we need to remember that. If we forget that big picture idea, this is not going to make sense here. So inverse trig is used to calculate an angle. So we're going to start with the inner trig function, and we're going to try to set up a right triangle diagram for it. If the inner trig function happens to contain inverse trig, which the one we're going to do does, it might help to set up this right triangle diagram. It might help to think of the inverse trig with regular trig. Right? Any equation you write with inverse trig, you could rewrite it with regular trig. Right? We can change it. Right? So for now, we're going to forget about the outside function. Okay, the outside function is sine. It's the one all the way on the left. But that's not going to have any effect on what we do until the very end of the problem, the very last step. Okay, we have a lot of steps, well, a few steps we have to do before we look at sine. So let's start with the inner trig function. Inverse cosine of v equals. Now, when I do inverse cosine, what am I solving for? What is, when I take inverse cosine of something and get that answer represents we just said this. Yep.
An angle.
And yeah, it represents an angle. Do I know what angle this inverse cosine represents right now? No, because I don't know the number I'm plugging in to get the answer to the inverse cosine. Okay, so I don't know what angle it represents. But it is going to represent some angle. how do we generally represent angles that we don't know? Yeah?
With Greek letters.
With a Greek letter, yeah. So let's just say that when you do the inverse cosine, again, I don't know what v is, but if I did, when I plug it in, it's going to give me some angle. Okay, so the inverse cosine of v will equal an angle. What angle? I don't know. Now, I want to rewrite that formula that I have right there using regular trig. So I want to get rid of this inverse cosine. What could I do to get rid of inverse cosine? Yeah.
Take the cosine of inverse cosine.
Yeah, take the cosine. So what I'm doing right now is I'm not going to be able to get rid of all the trig, but I'm going to get rid of the inverse trig by taking the cosine of each side. So take the cosine of what's on the left. Remember, there's no multiplication in that entire problem. I'm just taking the cosine of each side. Now, cosine and inverse cosine cancel each other out, and I get v equals cosine theta. Now, this step might not make sense right away, but I want to make the left side a fraction, and you're going to see why in a minute. How can I make the left side of this a fraction? Yeah?
You just put v over 1.
Just put v over 1. You'll see why in a little bit. Now, I want to set up a right triangle diagram. I'm going to draw a right triangle. You can put theta wherever you want, because theta represents the angle that we're talking about in this problem. You can put it here. And what's the only thing that we know about theta right now? We do know one specific thing about it. Yeah?
It's a cube.
Okay, it's a q. What else do we know? Something that's written up there. Yeah?
The cosine of it equals v.
The cosine of it equals v. That's going to allow me to label the sides in this triangle. If I know that the cosine is v, what is the definition of cosine in a triangle? Yep.
Adjacent over hypotenuse.
Adjacent over hypotenuse. So in this problem, what would be the label we would use for adjacent? Yep.
V.
V. And what would be the label for the hypotenuse? Yep. 1. Exactly. So that diagram that we just drew represents our situation. We have an angle where the cosine comes out to v. Now we're at the last step. We want to take the sine of our diagram. What I just put a box around, that's the diagram. So take the sine of your diagram. What's the definition of sine? Yep.
Opposite over hypotenuse.
Opposite over hypotenuse. Well, the problem is I don't know opposite. How could I figure out the opposite side in that triangle? Yep.
Pythagorean theorem.
Right. I'm going to use Pythagorean theorem. You can temporarily call it something if you want. I guess you could just call it x. But we're going to have a formula for it in a minute. It's not going to be a number. It's going to have v in it. But we are going to have a formula. So x squared plus v squared equals 1 squared. And now solve for x. Okay, so I can bring the v squared to the other side and then take the square root. So x is the square root of 1 minus v squared. What's v? I don't know. I'm never going to know what v is in this problem. That's not really the point. just write down what x is. Square root of 1 minus v squared. Now I have every side of this triangle labeled, and I can find any trig function you want me to find. Specifically, you want a formula for sine. So the sine of my diagram is opposite over hypotenuse. And then I would divide by 1, because that's the hypotenuse, but that doesn't change anything. So that is the answer. So each of those formulas that you see up there will give you the exact same thing. Let's try it. Now, when I pick a number for v, it has to be in the domain of inverse cosine. So what is the restriction for a domain of inverse cosine? -1 to 1. So I'm going to pick a random number. Let's do 0.37. Right? Something between -1 and 1. I'm going to take the sine of the inverse cosine of 0.37. And that's what I get. Now, plug 0.37 into that other formula we just found in the green box. Square root of 1 minus 0.37 squared. I get exactly the same thing. So what we just did is we found a formula that doesn't have any trig in it, and it gives you the exact same result as the formula that did have trig in it. Why would you want a formula without trig? Well, sometimes in calculus, working with trig is hard. So algebra can be easier, and we can get rid of all the trig. Just to show you that that's not random, let's pick another number, I don't know, let's do 0.76. Take the sine of the inverse cosine of 0.76. That's what you get. Now plug 0.76 into our formula. 1 minus 0.76 squared. You get exactly the same. Yeah. Okay, we'll do 1 or 2 more of these, but that's the basic pattern all the time. Take your inner trig function, draw a diagram. Pythagorean theorem gives you the third side, and then look at the outer function and write down whatever it is that they want. All right, let's try this one. So it says write an algebraic expression that will give you the cosine of the inverse tangent. So I want a formula to calculate that, and I don't want any trig in the final answer. Now, one other thing that can happen that didn't happen here is you can end up with square roots in the bottom of a fraction. As always, if that happens, we need to fix it. All right, which function do I start with here? The inner or the outer? Yep.
Inner?
Yep, start with the inner function. And I know that that inner function is what kind of trig? Yep.
Inverse?
It's inverse trig. And when you do inverse trig, the answer is always and. It's always the answer to an inverse trig problem. Like what kind of thing is it giving you the answer for in a triangle? Yep. An angle. What angle? We don't know. And we're never going to know. We never figured out this angle in the whole problem. We don't need to. Because the point is, the formula we're coming up with works for any angle. It's not just certain angles, it's all of them. Okay, so we know that when we do the inverse tangent of x, it's going to be equal to an angle, some angle. And now, what do I do to that equation to get it ready to draw in a diagram? Yeah?
Use tangent to cancel out the inverse.
Yep, we're going to take the tangent of both sides. And now you know that the tangent of your angle is x. So we need to draw a diagram. And you need to set it up so that when you take the tangent of that angle, you get x. Can anyone tell me how I could label the sides? Yeah.
The opposite would be x.
Yep.
And then adjacent would be 1.
Perfect. Are there other ways to label the sides? Absolutely. You could label the sides any way you want, as long as when you divide opposite by adjacent, you get x. Usually using a 1 is the simplest way. So opposite is x, adjacent is 1. This part represents my diagram. They want the cosine of my diagram. So what other side am I going to need to get cosine? Yep. Hypotenuse. And that's going to be the square root of x squared plus 1. Okay, that's what you get when you use Pythagorean theorem. So whatever letter they use here, that's the letter you should be using in your triangle. Okay. They used a V before, so I used a V. The letter doesn't matter. It doesn't change how you do anything. It's just a different letter. All right, so now we're ready to find the cosine. What's the definition of cosine? Yep. Adjacent over hypotenuse. Okay, so that is the formula. This formula right here will give you the same result as taking the cosine of the inverse tangent. But what's wrong with that formula? Yep.
You can't have square root.
Yeah, we shouldn't leave that in the bottom. So I'm going to fix it when I write the final answer by multiplying top and bottom by the root. And then, so when you multiply the top, you get square root of x squared plus 1. And in the bottom, you get x squared plus 1. Okay, this one I'm not going to check, but if you wanted to, you could pick a number for x that's in the domain of inverse tangent. What is the domain of inverse tangent? Yep. All real numbers. Just picture how that works. Goes left and right forever. So you can pick any number you want for x, plug it in, get the answer. Take that same number, plug it in for x over here, and you should get the same answer. Just like we did on the last one. Any question on that? All right, let's try this one. So this one says to evaluate without a calculator. So if we are evaluating it without a calculator, then that means the answer probably comes out nice. Somehow it's going to come out nice. Okay, what we're going to do, we're going to start with the inside function. This time the inside function is not inverse trig. Well, that's fine. Doesn't always have to be inverse trig. This one's regular trig. So we're going to try to actually figure out what is the tangent of 3 pi over 4. We're going to try to figure that out. And to figure that out, we need the unit circle. So 3 pi over 4, that's a multiple of what number? Thinking in terms of our unit circle. Yep.
Multiple 45.
Yes, it's a multiple of 45. Specifically, it's 45 times 3, because pi over 4 is 45, and we're multiplying 45 times 3. What's 45 times 3? I'm doing that because it might help to think of this in degrees, just to visualize it. 135. Okay. Where's 135 on my unit circle? Yeah?
Quadrant 2.
Quadrant 2, right in the middle of the quadrant, or closer to the x-axis or the y-axis?
Right in the middle.
Right in the middle. A 45 is always right in the middle. So here's 135. So you're looking at this angle right there. So what we do is we draw a reference triangle in quadrant 2. And that's a 45, 45, 90. How long is each side in a 45, 45, 90? I mean, how long is each leg? I know the hypotenuse is 1. But what's the length of each leg in a 45, 45 on a unit circle? Yep, both root 2 over 2. Now, we need the coordinate for 135, because we're trying to use unit circle trig to get this answer. What is the coordinate for 135 degrees? Yep. Good. Negative root 2 over 2. Root 2 over 2. Okay, so now we've got the coordinate for 135. What is the formula for tangent? And I don't mean opposite over adjacent. I mean like on the unit circle. What's the formula for tangent? Yep.
Y over X.
Perfect. Y over X. And what do you get if you divide the Y value of the coordinate by the X value here? Yep. -1, because Y and the X value are opposites. So now we figured out the inside function. Tangent of 3 pi over 4 is -1. Okay, so we just made the problem a little bit simpler. We need the inverse sine of -1. Okay. So we're doing inverse sine. What am I solving for? Like when I get my final answer to this problem, it's going to be what? Like it's measuring what? The final answer. Yep. It's measuring an angle because I'm doing inverse trig. So when I do this out, I don't know what it is yet, but I know it's going to equal some angle. And that's my answer I need to figure out. What is the angle in this problem? Well, if it's hard to think of this using inverse trig, then no. Let's think of it with regular trig. How could I get rid of inverse sine? Yep. Take the sine of it. If you take the sine of both sides, you end up with that. You end up with -1 on the left and sine theta on the right. Now, try to visualize what that would look like if you graphed it. You're going to graph sine in y1 like in your head. You're going to graph -1 in y2. Here's sine. And here's a graph of y equals -1, right there. What would you be looking for in that graph to find the answer? Yep, where it intersects. They intersect. You're trying to find where sine hits -1. Well, from that graph, it hits -1 right there. We just need to know what that point is. What is the x value? I mean, I know the y value of that point is -1, but what's the x value of this coordinate in radians? Yep. 3 pi over 2. And that is your final answer. If they wanted degrees, you could put 270 degrees. Right, so that's a good problem because it really ties together a lot of things. You have to know the unit circle, the formulas on the unit circle, and then you have to know what the graph of sine looks like and where sine hits -1. Now, it hits it again, too. If I were to draw this wave forever, it hits it infinitely many times. I just wrote down the first positive answer. If you wanted to represent all answers, you could do like plus the period times n, but that's not something we're looking at right now. Okay. Any questions on how we figured that out? Let's try this one. This problem is similar more to the first two types that we did, but the difference is you don't have a variable here. So it's actually easier. You have all numbers. So eventually when we set this up, the diagram will be all numbers. Now, what I do a lot of times is I don't do this step in the middle. I just draw my triangle right away. Can anybody, without breaking it down as much as we have been before, tell me what two sides have they really given me to label in this triangle? They've given me the what and the what? Yeah?
Opposite and adjacent.
Right, they've given me the opposite and they've given me the adjacent. Because if you labeled this like we did before, you would have something like tangent theta equals 1 over 2. That's what you would really have if you just took this part and took the tangent of each side. You'd have tangent of theta equals 1 over 2. Which one is the opposite? The 1 or the 2? Yep, the 1. So this diagram that I just drew represents this. Now, what trig function do they really want to know from that diagram? Yeah, they want to know the cosine. So what do I have to do to figure out the cosine in that diagram? Yeah. Right, I need the Pythagorean theorem because I don't have the hypotenuse. What's the hypotenuse going to be here? Yep. Square root of 5. So this is just like what we did in the first two problems, but I actually think it's easier to understand because there's all numbers. You don't have any letters this time. So your final answer is going to be a number. All right, so now they want the cosine of the inverse tangent. What would the cosine of the inverse tangent of 1/2 be? Lens?
Maybe that was square root of 5 over 5.
I think, oh, you did sine of the inverse tangent of 1/2.
I see.
But you had the right idea. You just did sine, not cosine. Yeah? Right, it would be 2 root 5 over 5. Because cosine is adjacent over hypotenuse. And then we fix the root in the bottom. And that's your answer, 2 root 5 over 5. Now, you might be thinking, well, why do I have to do that if I can just do cosine inverse tangent of 0.5 and get the answer that way? Well, why do you think doing it that way might be important? Yeah?
Because it's exact.
It's exact. There's no way you're going to be able to get the exact answer to that problem using a calculator. Okay, you can't do it. You could check it. 2 square root of 5 divided by 5. Yeah, we did it right. But you're never going to know that 0.894427191 is 2 root 5 over 5. So any questions on how to do it using that diagram and getting the exact answer? Okay, so that's a couple examples of how you can evaluate a trig function, or if it's a variable, write an algebraic expression that converts your formula to something without trig. This one would be another one similar to this one. Actually, no, similar to this one. It's exactly the same kind of problem. Anybody want to see that one? You draw your triangle, you label your opposite as 1, hypotenuse is 2, use Pythagorean theorem to get the adjacent side, and then do your cosine. If you end up with a root in the bottom, make sure we fix it. Okay, but there's no difference between that and example B. Okay. So let's look at this. So we're going to look at something we've kind of done before, solving trig equations. Remember that trig equations are periodic. So if they ask you for all solutions, I think I said this once today already, what do you have to put on the end of your solution to represent all solutions? Yep.
So plus period.
Plus the period end. Yep. So we put that on the end to indicate all solutions because there's infinitely many. You can't write them all down. You need a way to represent what they are because you can't write them all. What's the formula to find the period of, let's see what kind of functions we're going to get. Sine, and do we have a tangent in here somewhere? Yeah, cotangent. What's the formula for the period of sine? Usually I wrote that as t equals. That's the letter that our book used. Actually, sine, cosine, secant, and cosecant all use the same formula. Anyone remember it? It's a fraction, something over something. Yep.
2 pi over b.
Yes. Sine, cosine, secant, and cosecant use 2 pi over b. What's the formula that tangent and cotangent use? Yep. Pi over b. Okay. If we don't know those two, then we're not going to be able to set a window if that's something we're doing on the calculator. We wouldn't be able to figure that out. Even if we're not setting a window, we wouldn't know what our answers are supposed to be between. Because generally, they ask you to find one cycle worth of answers, and then put plus period times n. If we are typing something in on the calculator, we may have to use a reciprocal identity because we don't have a secant, a cosecant, or a cotangent button. And we are going to do I just looked at it, we're doing a cotangent. So you have to know how to put that in on the calculator. All right, so let's try example. Okay, first of all, it says find all. At this point, you should be able to visualize in your head what sine looks like, what y equals 0.6 looks like, and estimate how many solutions there are per cycle. Because there's no transformations to this. If you start throwing in transformations, that can complicate it to do in your head. But how many answers are there going to be per cycle in this problem? Yep. 2, right? You're going to have a wave and a horizontal line. It's going to hit it twice. The only way it hits it once is if it hits at the max or the min, which would be 1 or -1. This is right in the middle, so it's going to hit the wave twice. Kind of like this. Something like that. Let's do this 2 ways. Let's do it with the calculator, and then we'll do it without. Okay, so to do it with the calculator, that part's pretty straightforward. I'm going to put in sine of x. I'm going to put in 0.6. and I need to set my window to 1 cycle. Okay? We just said the cycle length is, the formula is 2 pi over b. What's b in this case in my sine function? Yeah, 1. There's no number in front of x, so it's just a 1. So I want to set the period to go 1 cycle. Easy way to do that is 0 to 2 pi. That will show you 1 cycle. Make sure you're at least negative 1 to 1. I would do negative 2 to 2 on the y. Okay, so here's your graph. And now we'll just do second calc intersect. I'm going to do the one on the left. If someone else can do the one on the right, that will save us a couple seconds. So the one on the left is 0.644. Call x1 and x2. And what's the one that was on the right? Yeah.
2.5.
Can you give me 3 decimal places?
2.498.
2.498. Okay, perfect. Now, if that's what I do, I haven't answered the question all. All I've done is find 2 answers. What would I do there to represent all of them? Yep.
Plus 2 pi n.
Plus 2 pi n. Okay, so that's how we can do it graphically. But we've already seen some problems doing things graphically. You don't always get an exact answer. Okay? This one wouldn't come out to an exact answer either way. But maybe if we wanted to do it algebraically, you don't have access to a graphing calculator. You might have to do it algebraically. So let's take that equation. How would you get the x by itself on the left side? What would you have to do? Yeah?
Take the inverse sine.
Yeah, actually, let me put it over here. Take the inverse sine. Take the inverse sine of what's on the left, inverse sine of what's on the right. Second, inverse sine, 0.6. I actually think that's faster than graphing. 0.644. That's my first answer, and that's exactly what I got right there. 0.644. Now, the second answer. For the second answer, I've got to show you how you figure that out. Once you know what I'm about to show you, it's very easy to get that second answer. It's going to be pi minus the first answer, 0.644. I'm going to use this diagram. Okay, don't think this is a diagram I've shown you before. But what this diagram is showing you is where each trig function comes out positive. So in quadrant 1, all trig functions are positive. Sine, the cosine, the tangent, and of course the reciprocals. Because if you flip something, if it started as positive and you flip it, it's still positive. In quadrant 2, quadrant 2 represents all the angles between 90 and 180. If you take the sine of any angle between 90 and 180, it will come out positive. Everything else is negative. In quadrant 3, those are the angles between 180 and 270. The only trig functions that come out positive in quadrant 3 are tangents. And of course cotangents, because you flip it and it's still positive. Okay. But everything else in quadrant 3, sine, cosine will be a negative. And in quadrant 4, those represent the angles between 270 and 360. The only ones that come out positive in quadrant 4 are cosine. So ASTC, that's the diagram you can use to remember it. Sometimes people try to come up with like an acronym, like all students take calculus, or I don't know, I think that's one that people use. All students take calculus, ASTC. That's not actually true, but it works. So now, in the second quadrant, there was a formula that we had in the third quadrant and the fourth quadrant, and it dealt with the reference angle. Does anybody remember the formula that we used in quadrant 2 to find an answer when we knew a reference angle? If you're not sure, think about, like, if you wanted to know this angle from here to here, but you knew that reference angle right there, what would you do to find that arc in red? Yep.
Just 180 minus the angle.
Yep, 180 minus the angle, or pi minus the reference angle. That was the formula, and that I did tell you before. That was in quadrant 2. Does anyone remember the formula for quadrant 3? Yep.
Pi plus reference.
Yep, pi plus the reference angle. And what about the formula for quadrant 4? Think about if you had a triangle like that, and you knew that angle right there, and you were trying to find that. What would you do in quadrant 4?
360 minus the reference.
Yep, it's basically all the way around, but then you back off the amount of your reference angle. So 360 minus the reference angle. So those formulas I gave you before, but I didn't give you the ASTC. Now, combining those two together gives us a very, very fast way to get the second answer to this problem after we already have the first answer. Look at the original problem. It says sine of x equals 0.6. Is 0.6 a positive number or a negative number? Yeah? Positive. And it's equal to the sine function. So you're looking for where the sine function is a positive number. What two quadrants does sine come out positive? Yep. 1 and 2. We already have an answer in quadrant 1. 0.644. How do I know that's in quadrant 1? Well, in radians, this is 0 to pi over 2. That's 0 to 1.57. This is in that range. What I need is the quadrant 2 answer. What's the formula to find an angle in quadrant 2? Yep.
Pi minus the reference angle.
This is your reference angle. Your first answer. Pi minus 0.644. So if we take pi minus 0.644, you get 2.498. It's exactly the same answer we got before. Once you know this chart, and you have that memorized, I think it's faster than graphing. Because you don't have to worry about setting a window, the x-min, x-max, y-min, y-max. You don't have to do second calc intersect. You don't need a graphing calculator at all. So let's try cotangent. We'll do it the same way. We'll do it algebraically and graphically. All right. What would I put in y1 if I want to graph cotangent? And there's a couple ways you can do it. It's one way I'm thinking of. Yep.
1 divided by 2.
Yeah, you could do 1 divided by tangent. The other way is cosine divided by sine. That's the same thing. So we got 1 over tangent. And in y2, we're going to do 2.5. What is the period of cotangent? No transformations at all. Just basic period of cotangent. Yeah. Pi. So what could I set for a window so that it's exactly pi units wide? Yep.
0 to pi.
I could do 0 to pi. Now, with tangent, you might cut off a cycle in the middle. That's okay. Doesn't matter if we do that. We didn't. Now, I don't see anything because I forgot to change something. What do I need to change so I can see what's happening here?
The y.
Can you be more specific?
Yeah.
Yes, my y max is not high enough. Let's put it at 3. Now we'll be good. Okay. So first question, how many answers do we get per cycle? Yeah, 1. There's 1 answer per cycle. 0.381. And then what am I going to put on the end of it to indicate that that answer repeats? Yeah? Plus pi n. Okay, so that's graphically. And now let's look at it algebraically. How can we get x by itself here? What would we have to do on both sides? Well, what function are we trying to get rid of? Cotangent. What function do you, we haven't really specifically talked about this, but what function do you think would cancel out cotangent? Yeah?
Maybe tangent.
No, tangent doesn't cancel out cotangent. They're reciprocals. Yeah? Inverse cotangent. Well, we don't have an inverse cotangent button. So we can't quite do it that way. But if we know the cotangent, what other function do you automatically know? There's a connection between this function and cotangent. Yeah?
1 over tangent.
So what trig function do we know? I'm looking for just a single trig function without any numbers in it. You know the cotangent, and you also know the one over tangent is just cotangent. That's the same thing as cotangent. So think about when we wrote these down, we wrote 6 of them at a time. Cotangent was across from which one? Yeah, tangent. So if the cotangent is 2.5, what's the tangent? Yeah. 1 over 2.5, exactly. So now we've just rewritten that problem with a trig function. We do have a button for it on the calculator. So the tangent is 1 over 2.5. And now what trig function could we use on both sides to get x by itself? Yeah,
The inverse of tangent.
right. Take the inverse tangent on both sides. Okay, let's do that and see what we get. Inverse tangent of 1 divided by 2.5 comes out to 0.381. 0.381, exactly the same thing. Now, usually that diagram I just showed you gives you two answers. Well, let's think about what's happening there. We're looking for where cotangent is positive. That's the same as looking for where tangent is positive. Same thing. What two quadrants is tangent positive in? Yeah? The first and the third. 0, pi over 2, pi, 3 pi over 2, and this would be 2 pi. 0.381. That's in quadrant 1. There is another answer in quadrant 3. Why don't I need to write it down? The other answer is pi plus my reference angle. So if I took pi and I added 0.381, well, pi plus 0.381, that is the other answer. 3.522 or 3.523. Why wouldn't I write that answer down? 3.523. Just put it there for a second. Yeah?
It's in a different cycle.
It's in a different cycle. This answer is already included right there. If you add one multiple of pi to 0.381, you automatically get that answer. It's in another cycle, so you don't need to write it down. What we did up here, these two answers were totally separate. You have to write both of them. But down here, we did not. So any questions on that? There's a lot of things that are starting to come together with trig, from circle, reciprocals, this diagram with the ASTC, that's new that I added today. These things all kind of have to start coming together in chapter 7. Because we're going to use a lot of them the rest of the week. All right, so homework, it's not a ton of problems. So it's 394. We'll look at that tomorrow, and then we'll do, let's see, we just did 7.2. So 7.3 tomorrow, and then 7.4 on Thursday.